Now we go to the next level of retardation, and that I am going to call in general damping. And usually when I talk about damping in oscillations, I mean a term which is proportional to velocity. So there is a retardation or damping force which is proportional to the velocity and obviously opposite to the velocity. Let me write this in one dimension as minus b x dot, and therefore the equation of motion in this case is going to be mx double dot is equal to minus kx minus bx dot, which I can write as mx double dot, bringing all the terms x terms to the left, bx dot plus kx is equal to 0. Dividing by m, I am going to write this as x double dot plus b over m x dot plus k over m x is equal to 0. This term I already identified as omega naught square. I am going to call this term gamma, or the damping coefficient, and therefore write this equation as x double dot plus gamma x dot plus omega 0 square x is equal to 0. This is the equation for a damped harmonic oscillator, where the damping is proportional to the velocity. And we will see how we get different solutions for this and different kinds of motion under separate circumstances. So the two roots for this equation, x double dot plus gamma x dot plus omega naught square x is equal to 0. When I assume a solution of the form e raised to lambda t, lambda that I get is minus gamma plus or minus the square root of gamma square minus 4 omega 0 square over 2, which I can write as minus gamma over 2 plus square root of gamma square by 4 minus omega 0 square, or the other root is minus gamma over 2 minus square root of gamma square over 4 minus omega 0 square. Depending on the relationship between gamma and omega, the motion is going to be different. For example, if gamma square by 4 is greater than omega 0 square, in that case I am going to have no imaginary part in the roots, and therefore solution is not going to be of the oscillatory nature. On the other hand, if gamma square over 4 is less than omega 0 square, I am going to have an I imaginary part in the roots, and that is going to lead to oscillatory motion, as we saw in the undamped harmonic oscillator case. So let us examine these cases one by one. So I got two roots, lambda equals minus gamma over 2 plus square root of gamma square over 4 minus omega 0 square, or also minus gamma over 2 minus gamma square over 4 minus omega 0 square square root. Let me call this minus lambda 1, let me call this minus lambda 2, so that the solution in the case when gamma square over 4 is greater than omega 0 square, and this is important. Now I am going to focus on this. When this is so, lambda 1 and lambda 2 are real, and the general solution x t is going to be of the form c e raised to minus lambda 1 t plus d e raised to minus lambda 2 t. When gamma square over 4 is greater than omega 0 square, this case is known as the heavy damping case. You can see from this expression that the solution is not oscillatory anymore. So right now let us focus on heavy damping. Later we will see when gamma square over 4 is equal to omega 0 square, both lambda 1 and lambda 2 become equal. In that case there seems to be only one solution. We will obtain the other solution by taking the limit lambda 1 going to lambda 2, and that is known as critical damping. We will discuss that also. And finally, when gamma square over 4 is less than omega 0 square, that is known as light damping case. In that case, we will obtain oscillatory solution. So, right now let us focus on heavy damping case. In that case, the solution x t is of the form C e raised to minus lambda 1 t plus d e raised to minus lambda 2 t, where lambda 1, if you recall, is gamma over 2 minus square root of gamma square over 4 minus omega 0 square, and lambda 2 is gamma over 2 plus square root of gamma square over 4 plus omega 0 square, and this is the way it is defined is greater than lambda 1. I will study 3 cases in this case and see how the motion looks like. So, let me take case 1, where I take this spring mass system, stretch it and leave it, and let us see how the motion looks like in that case. So, what I am given in this case is that x at 0 is equal to some value a, which from the general solution is going to be c plus d. Recall that my general solution x t is equal to c e raised to minus lambda 1 t plus d e raised to minus lambda 2 t, lambda 2 greater than lambda 1. And since x dot at 0 time t equal to 0 is 0, this tells me that minus lambda 1 c minus lambda 2 d is going to be equal to 0. These are 2 equations that give me the coefficients c and d. From equation 2, I have d is equal to minus lambda 1 over lambda 2 c. Substituting this in equation 1, I get c minus lambda 1 over lambda 2 c is equal to a, or c equals lambda 2 a over lambda 2 minus lambda 1, and therefore, d equals minus lambda 1 a over lambda 2 minus lambda 1. I have obtained both the coefficient in the case when I pulled the mass out and let go, and therefore, the general solution in this case is going to be of the form c was lambda 2 over lambda 2 minus lambda 1 e raised to minus lambda 1 t minus lambda 1 e raised to minus lambda 2 t over lambda 2 minus lambda 1 times a. You can substitute c and d and see this is the solution, which is equal to a over lambda 2 minus lambda 1, lambda 2 e raised to minus lambda 1 t minus lambda 1 e raised to minus lambda 2 t. And keep in mind that lambda 2 is greater than lambda 1. This motion, if plotted, x t versus t, is going to look like I start with value a at time t equal to 0, and then it slowly decays. And how does it decay? Since lambda 2 is greater than lambda 1, as time becomes larger and larger, time goes towards infinity, this term is going to die down much faster than this term. So, it is going to decay at larger time as e raised to minus lambda 1 t. So, this is a solution. Let us now take a second situation in which I take this mass and give it an impulse, so that at x 0 equal to 0, it starts with a velocity x dot is equal to v in the positive direction. Again, looking at the general solution, x t equals c. So, this is my situation b, e raised to minus lambda 1 t plus d e raised to minus lambda 2 t. I have c plus d is equal to 0, and x dot, which is minus lambda 1 c minus lambda 2 d is equal to V. This is my equation 2. Substitute d equals minus c from here, I get minus lambda 1 c plus lambda 2 c is equal to V, or c equals V over lambda 2 minus lambda 1 is equal to minus d. And therefore, the solution in this case, when I am hitting the mass with an impulse, giving it an impulse or velocity v in the beginning, right at the equilibrium point, is going to be x t is equal to v over lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t. By plotting it, you can see that the solution is going to look like, initially the particle goes out and then it decays, its distance sort of decays exponentially. Again far away, since lambda 2 is greater than lambda 1, it decays as e raised to minus lambda 1 t. This is the second situation. Now let us take the most general situation, in which I take the mass, stretch it out, and also initially give it a velocity going n, v. Why I am doing that is, I want you to note that in the previous two situations the solutions were looking like this, so that the particle really never crossed the equilibrium point once it was released. It, in the first situation, it just slowly went towards the equilibrium point. In the second case, it went out and slowly started coming towards the equilibrium point. I want to see whether I can really cross the equilibrium point. So I am taking it out and pushing it in. Again the general solution, undamped oscillator x t, heavily damped oscillator, the solution is x t equals c e raised to minus lambda 1 t plus d e raised to minus lambda 2 t. And what I am doing is, at time t equal to 0, I am displacing it out and also giving it a velocity minus v. And let us see what happens. X t is equal to c e raised to minus lambda 1 t plus d e raised to minus lambda 2 t, and therefore I am going to have a is equal to c plus d. Similarly, x dot t is equal to minus lambda 1 c e raised to minus lambda 1 t minus lambda 2 d e raised to minus lambda 2 t, and when I take x dot 0 to be minus v, I get minus lambda 1 c minus lambda 2 d is equal to minus v. I have two equations and two unknowns. I can solve them. I leave it for you to work out, and you will see that the general solution in this case comes out to be minus v over lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t plus a over lambda 2 minus lambda 1 times lambda 2 e raised to minus lambda 1 t minus lambda 1 e raised to minus lambda 2 t. Let me write this solution neatly on the next page. X t in this case, when I have taken the block out and then pushed it in with a velocity, comes out to be minus v, minus because I am pushing it in, divided by lambda 2 minus lambda 1 e raised to minus lambda 1 t minus e raised to minus lambda 2 t plus a over lambda 2 minus lambda 1 lambda 2 e raised to minus lambda 1 t minus lambda 1 e raised to minus lambda 2 t. And when I plot the solution, in general it is going to look like this. It starts with a value a, goes down, goes to the negative side, and then after that decays, solution decays like this. So this is one case where the mass does cross the equilibrium point but once it reaches the left hand side maximum stretch, it again the solution decays exponentially. So, we conclude that in heavy damping case, the particle can cross the equilibrium point at most once, and then far away the solution decays as e raised to minus lambda 1 t. So, when time becomes large, slowly the particle comes towards the equilibrium point. This is the case of heavy damping. Let us summarize this. In the case when I stretched it and let go, the solution looked like something like this. X t slowly decayed towards 0, that means the mass slowly came towards the equilibrium point. The second case, when I took the mass and gave it an impulse, the mass went out and then again slowly it started approaching the equilibrium point. And the third case, where I stretched it and then gave it a velocity also, in that case in general the mass crossed the equilibrium point and then finally slowly approached towards the equilibrium point. These are the cases where lambda 1 was not equal to lambda 2 and what we called heavy damping.